today we will discuss the concept of Cauchy sequence and completeness. The convergence concept we already discussed. However, we will repeat what we have done it last time. We know the sequence of the real or complex number, it plays a vital role in calculus, and the metric defined on it, that is the usual matrix, enables us to define the concept of the convergence. When we say a sequence of the real or a complex number n goes to a, it means the difference between a n minus a, this tends to 0 as n tends to infinity. So, this basically difference is nothing but the distance between a n and a, and this concept on the real line we wanted to enhance over an arbitrary metric space x t, where x is the set of point and d is the notion of the distance defined on it. So, we say a sequence x n, a sequence convergence first, a sequence x n in a metric space x d is said to converge or to be convergent if there is an x belonging to capital X such that the distance between x and x when n is sufficiently large is tending to 0 or limit of this is 0. There x is called the limit of the sequence x n, and we write of course write it as x n goes to x under the limit when n tends to infinity, under the limit of this. Now, here if we look this, what is d of x n x? It is basically a real number. It is basically a real number, a sequence of the real number. So, the concept of the sequence of that real number, the same concept here is applied. We are converting the sequence points in x n in x, which goes to x in the form of the real number, and then applying the same definition of the convergence of a real or complex numbers, real numbers. Now, here when we say the x n converges to x, this means here we say an x n converges to x means for given epsilon r greater than 0, there exists an integer n which depends on epsilon r such that all x n with n greater than capital N lie in the neighborhood, in the epsilon neighborhood of x, that is in epsilon neighborhood V x epsilon of x. That is the meaning of this here. So, in terms of the neighborhood we can say sequence x n converges. Okay. Now, the point x must be a point in x, that if x does not belongs to capital X, then we cannot say the limit converges. For example, if we take a sequence x n, say 1 by n, and our capital X is a semi-closed interval 0 to 1, and the metric d if I take as x minus y, then though the sequence x n goes to 0 when n tends to infinity in the sense of real over a real line, but the 0 is a point which is not available in the space X. So, we say the x n does not converge to 0 in the metric space X t, because the limiting point is not available here. Okay. So, the important part is here that limiting point must be a point of the space X. Okay. That is why the convergence of a sequence is not an intrinsic property. It basically depends on the metric on the space which you are choosing here. Okay. If I take this closed interval, then the same sequence will behave as a convergence sequence in this space. So, this much we have already discussed earlier. Now, based on this or using this concept of the convergence, we can now define the concept of the boundedness and the relation between the convergence and the bounded sequence. So, boundedness. Bounded. A non-empty subset M of x is said to be bounded to be a bounded set if its diameter delta m, which is equal to supremum d of x by x, y, all the points of m is finite. Okay. So, a set M, which is a subset of a metric space X d, is said to be bounded if the diameter of this set is finite. That is, if we pick up any 2 points here, find out the distances, and like this if we continue, then supremum of this, if it comes out to be finite, then we say the set M is bounded. And similarly, we say a sequence x n in a metric space X d is bounded, is said to be bounded if the corresponding point set, that is x 1 comma x 2 and so on, is a bounded set, is a bounded set, bounded subset or set subset of x. So, basically what we get, if so clearly if a set M is bounded, then M can be contained inside a open ball centered at x naught with a suitable radius r, where x naught is a point in capital X and any point in capital X, and r is sufficiently large real number. If we have this set X d, a metric space, and this is our set M, if this set is bounded, it means if I pick up any arbitrary point x naught in capital X, need not be, then corresponding to this point we can always find a open ball centered at this point with a suitable radius say r, such that all the points of the set M are the points of this ball. Then we say the set M is a bounded set or bounded subset of X. Okay. So, there is a relation between the convergence and bounded sequence. So, we go for some relation in the form theorem, or let it be, let X, which is a metric space X D, be a metric space. Then the following thing holds: a convergence sequence in X is bounded and its limit is unique. This is the first assertion we made it. Second point which is true, if sequence x n converges to x and y n converges to y in the metric space x d, then the corresponding distances x n by n, this will go to d of x y. Okay, this. So, basically what this result says, every convergence sequence is a bounded sequence. We are not talking about the converse part. Converse is basically not true always. In general, the bounded sequence need not be a convergent always. Okay. Second part says, if there are two sequences which goes to the limit x n y, then the difference, if I take the x n by n and find out the distances, then that distance will also go to the distance between x and y. So, that is what is. So, let us see the proof of this. Part A, what is given is a convergence sequence is given. We wanted to show the convergence sequence is bounded. So, suppose sequence x n converges to x. Okay, this is given. So, by definition of the convergence, so for given f signal, say suppose 1, we can find an n, an integer n, such that distance between x n and x can be made less than epsilon, that is 1, after certain integer capital N. So, all n greater than capital N. So, let us consider d of x n comma x. We claim that this is less than 1 plus a, where a stands for maximum of d x 1 comma x, d x 2 comma x, d x n comma x. So, if this is true, then obviously a point set x 1 x 2 x n will be a bounded set, because d of x n x is less than 1. So, suprema was taken is finite, therefore, the convergence sequence will be a bounded sequence. Okay. Now, how does it follow this? By the triangular unitarity, we can write d of x n x when n is, say n is less than or equal to n. We can write this thing as, this will be less than equal to d of x n comma x n minus 1 plus d of x n minus 1 comma x n minus 2, and lastly it goes to d of x1 comma x, like this. So, here when n is there, so we can write this as capital N also. So, we can say capital N, that is goes at d of x comma x, x n minus 1, and d of x n minus 1, x n minus 2, and like this continue fill d of x 1 comma x. Now, the maximum value of this say a, then we can write this is less than equal to some n times a. So, let it be another constant, say a 1. Okay. So, we can say d of x n x is less than a 1 for all n 1 to up to n minus 1 or n up to n, and for n greater than this one n, it is already less than 1. So, basically when you take the both this simultaneously, we can write that d of x and x is less than 1 plus a for all n this way. This is true for all n, for all n, for every n. This is true. So, it is, so we get this shows that sequence x n is bounded. Okay. Now, second part of this is the limit is unique. So, for the second part, suppose x n has its two limit. Suppose x n converges to x and also x n converges to z. We wanted x and z are identical, equal. So, now consider d of x comma z. Since the distance cannot be negative, it will always be greater than equal to 0. Apply the triangular inequality. So, we get d of x comma x n plus d of x n comma z. Now, as n tends to infinity, x n converges to x as well as x n converges to z is our assumption. So, the right hand side will go to 0. Therefore, this d of x z is less than equal to 0, but basically it is always greater than 0. So, this implies d of x z is 0, that implies x equal to z by definition of the matrix. So, limit will always be unique. If a sequence converges, it will converge to the same limit. Okay. So, this the second part of it proof that we wanted to show that if x n converges to x, by n converges to y, then d of x n by n will go to d of x y. So, consider d of x n by n. Start with this and then apply that triangular inequality d of x n comma x plus d of x comma y plus d of y comma y. Okay. Now, transfer this d of x y this side. So, we get d of x n y n minus d of x y is less than equal to d of x n comma x plus d of y n comma y, because it is symmetric in nature. Now, as n tends to infinity, the right hand side tends to 0. Okay. Right hand side will go to 0, because this goes to 0, this goes to, so this will go to 0. Now, interchange the role of x n and x, that is x n is interchange with x, by n interchange with y. Then here you are getting d of x y minus d of x n by n, and this can be further written, because if I interchange x and x, there is no change. So, this will also go to 0 as n tends to infinity. Okay. So, what we get it from here, d of x n by n minus d x y tends to 0, while in this case d of x y minus d of x n by n goes to 0. This implies the modulus of d x n yn minus d of x by this modulus will go to 0 as n tends to infinity. Okay? And that is what we wanted to prove. Okay? Clear? Now, so far we have considered the convergence of the sequence and the corresponding sequence set to be bounded set and the relation between the convergent and bounded. The converse of this, converse of part A need not or be true always. That is, every bounded sequence need not be convergent, need not be a convergent sequence. For example, if I take a sequence x n to be minus 1 to the power n by say n. Okay. Now, obviously, this sequence when or just we take minus 1 to the power n, clear, this is convergent, we can say minus 1 to the power n. Take the sequence x n to be minus 1 to the power n. Now, this sequence is not convergent. Sequence minus 1 to the power n is not convergent as n tends to infinity, because when n is say even it goes to plus 1, when n is odd it goes to minus 1. So, it is not a convergent, but it is a bounded sequence. Of real numbers. So, every bounded sequence need not be convergent, that is. Now, another concept which we wanted to introduce is the completeness. The completeness concept is not derived with the help of that 4 properties which the metric enjoy. That is, the Aubry metric space d of x by is greater than equal to 0, real, non-negative and positive real finite number. It is 0 when it is x equal to y and vice versa, d of x y equal to d by x and d of x y is less than equal to dx z plus d of z by. So, these properties are satisfying, then only we say the metric is the d is a metric on x, but it does not give any information, it does not say whether the metric is complete or not. So, before going the definition of the completeness, let us see what is the meaning of this completeness in a general metric space and how can we show, how can we prove the metric is a complete metric space. But this is a different property, this is an extra property which the metric enjoy. Some of the metric spaces are complete, where there are examples where the metrics are also in complete metric space. The concept of the completeness is taken basically from the sequence of the real number or sequence of the complex number. We know that sequence of the real number or complex number, if it is convergent, it will satisfy the Cauchy convergence criteria. What is that Cauchy convergence criteria? So, you can say a sequence x n, we know a sequence x n of real or complex number converges on the real line R or in the complex plane C if and only if if and only if for every given f signer there is an n which depends on f signer such that mod of x n minus x m is less than f signer for all n and m greater than n. Okay. Now, this mod of x n minus x m is less than f signer. This is equivalent to basically the distance between x n and x m in a real line or complex plane, because distance, notion of distance on real or complex plane is defined as the usual way, mod of x n minus x m. So, when we say a sequence x n of real or complex number is convergent, if and only if for any f signer they are greater than 0, there exists n such that the distance between x and m is less than f signer, and this criteria is known as the Cauchy convergence criteria. Okay. Or we say if a sequence satisfies this condition, then we say it is a Cauchy sequence. Or we say if a sequence x n of real or complex number satisfy the condition of Cauchy criteria, then such a sequence we call such sequence x n as a Cauchy sequence. So, we can also say a real sequence of real or complex number converges. So, we can say a sequence of real or complex number converges on R or C if and only if it is a Cauchy sequence. It is a Cauchy sequence. Okay. So, this is the criteria is well known, and we know all the sequence of real complex number. If a convergent, it will be Cauchy and vice versa. Clear? And that is why we say the real or complex number is a complete space. But in general metric space, this criteria may not hold good. A sequence x n in X may be a convergent sequence, may be a Cauchy sequence, but need not be convergent. For example, if we take the earlier sequence x n to be 1 by n, which we have discussed, and metric, if I take the usual metric and x to be 0 and 1, where 0 is omitted, then we have seen the sequence is not convergent. However, that can be shown to be a Cauchy sequence. So, such a space we cannot say it is a complete. So, we define the completeness related to this a sequence which is Cauchy or not a Cauchy sequence. Okay. So, before going this, let us see the definition of the Cauchy sequence in a general metric space. A sequence in a metric space x d is said to be Cauchy, or we also say fundamental sequence if for every if for every epsilon greater than 0 there is an n depends on epsilon such that distance d of x m comma x n is less than epsilon for every m n greater than n. Okay. And the space X is said to be complete. So, definition of a complete metric space. A metric space X D is said to be complete if every Cauchy sequence in X converges. That is, the limit point, that is, has a limit point, has a limit which is an element of X. Of X. Okay, which is an element of X. So, a metric space is said to be complete if every Cauchy sequence in X converges, that it has a limit which is an element of X. So, obviously, with this definition one can say the set of real number or set of complex number under the usual metric is a complete metric space, because a Cauchy convergence criteria said every sequence of the real or complex number is Cauchy, or if a sequence is Cauchy it must be convergent, okay, vice versa both there, clear. So, that is, but in general metric space whether it is true or not, let us see. So, example is, if I take a metric space X to be 0 1 and d of x by h mod of x minus y and take a sequence x n to be 1 by n of real number, then clearly sequence x n is a Cauchy sequence, because the difference between two terms of the sequence can be made less than epsilon r after certain integer n m greater than for n m greater than equal to n. It can be so. Okay. 1 by n minus 1 when n m sufficiently large, it basically reducing to 0. So, we can identify the capital N such that after certain stage the difference between these two terms can be made as small as we please. So, it is a Cauchy sequence, but the limit of the sequence x n 1 by n, this tends to 0 as n goes to infinity, which is not in X, because X is the semi-closed interval 0 and 1. Therefore, this Cauchy sequence is not convergent. So, this space X under D is an incomplete metric space, incomplete. In fact, those space where all the Cauchy sequences are not convergent, the space will be incomplete. That is, if there exists even a single Cauchy sequence which is incomplete, which is not convergent, then it will be an incomplete metric space. Okay. Okay. There are many examples others also for an incomplete metric space. If I take the space X to be R minus A and the notion of the distance d x by, if I choose to be mod of x minus y, then we see that this space is an incomplete metric space, because we can choose a sequence x n which is of the form say a plus 1 by n, then this sequence is a Cauchy sequence which converges to a as n tends to infinity, while a is not a point edge, a does not belongs to the space x, where a does not belongs to this. So, it is incomplete metric space. Then another example we can choose from the set of real number. If I remove or take out all the rational point, then the set of rational number is in complete metric space. Okay. Even the open interval under this metric dx by as mod x minus y with a induced topology will be a incomplete metric space, because here I can choose the sequence x n as a plus 1 by n, or x n we can choose to be b minus 1 by n. This type of sequence if I take, then both are Cauchy sequences, what does not or do not converge. Okay. Converge. So, that is why it is a not okay. Now, what is the relation between the convergence and the Cauchy sequence? Every convergence sequence is a Cauchy sequence, that we will show, and Cauchy sequence need not be convergent. We have already seen by many examples where the sequence are Cauchy, but not convergent. So, we have result. Every convergence sequence in a metric space x d is a Cauchy sequence. Is a Cauchy sequence. The proof is very simple. Suppose we have a sequence x n which converges to x. So, by a definition, for given epsilon greater than 0, there exists an n depending on epsilon such that the distance between x n comma x can be made less than epsilon or epsilon by 2 for all n greater than equal to say capital N 1. Okay. Then similarly, we can say a sequence say x m converges to x. Okay. We can say for the given epsilon greater than 0, there exists say here n 1. So, I am taking here n 1, here n 2 depending on epsilon such that d of x m comma x is less than epsilon by 2 for all n greater than equal to. Now, if I picked up n to be maximum of n 1 comma n 2, then both these conditions holds for all n m greater than equal to capital N. This is also less than epsilon by 2, this is also less than. So, consider d of x n comma x n. Now, this will be less than equal to d of x n comma x plus d of x comma x n. Now, this is less than epsilon by 2, this is less than epsilon by 2 for all n m greater than or equal to capital N. Therefore, this whole thing will be less than epsilon, hence we say the sequence x n is a Cauchy sequence. So, this completes the proof. Okay. Converse we have already discussed. Now, second result which gives the relation between the closure and the convergence. The result is, let M be a non-empty subset of a metric space X T and M bar its closure. Then the following result hold: X belongs to M bar if and only if there is a sequence x n in M such that x n goes to x. B part A. M is closed if and only if the situation x n belongs to capital M, x n converges to x implies that x is a point of M. Okay. The proof is like that. So, if x is an M closure means set of all the points M together with its limit point. M closure means the set of all points of M together with its limit points, all limits points. Then this is the M closure. Okay. So, we will prove the first part, that is part A. What we want is x belongs to M bar, then there is a sequence x n in M such that. So, let us suppose x is a point in the closure of this. Okay. So, the possibility is either x will be a point in M or x may be limit point. So, if x is in M, then there is a sequence of the type x comma x etc. in M which converges to x. So, our result is follow. So, result follows. Okay. That is what we wanted to show. There will be a sequence x n in M which goes to x. There will be a sequence x n in M which converges to where x belongs to M. So, obviously, this x will be in M. So, this follows. Now, if as x is not in M, then it will be a limit point. Then it is a point of accumulation of M. So, if it is a point of accumulation, then for each n, say 1, 2, 3 and so on, the ball be centered at x with a radius say 1 by n contains an x n belongs to M, and this x n sequence will go to x because 1 by n is tending to 0 as n tends to infinity. So, again the assertion is complete. So, if x M is then there will be a sequence n such that x n converges to x. So, there will be okay. So, this problem. the part conversely we now have this. Suppose a sequence x n in M that goes to x, then we prove that x belongs to M closure. So, conversely, if the sequence x n is in M, okay, and x n goes to x, then there are two cases, either x will be a point of M or every neighborhood of x or every neighborhood of x contains points x n other than x, because this is a sequence goes to x. So, either x will be a point in M, okay, because x n are in M, or if it is not, then every neighborhood of x will contain the point x n which is different from x. So, this shows that x must be an accumulation point. Hence, x is a point of accumulation. So, it must be a point in M bar. Hence, x belongs to M closure, M bar by definition, closure of M. So, this the proof for the part B is very simple. It follows from part A. We know that M is closed if and only if M is equal to M closure. This we know. Now, if M is equal to M closure, so let us see the part A now. When M is closed, it means M is equal to M closure. So, if M is M closure, then according to the part A, there will be a sequence x n which goes to x. So, we get the sequence x n belongs to x, but the point x will be in M because M is closed. So, it will be the point of M bar, means it will be in M, okay, and vice versa. If I take this part, suppose x n is there, x n converges such that x belongs to M, then the x either it will be a limit point or will be a point of the M itself. So, it must be in M closure. So, M equal to M closure and M will be closed. Because all the limit points lies in M, it means M is equal to M closure, it means M will be closed. So, this completes the proof of this, nothing to prove. Okay. So, it proof, you can say proof follows from part A. Okay, that is complete. Okay. Now, there is another results. A subspace M of a complete metric space X is itself complete if and only if the set M is closed in X. So, what is the meaning of this? A subspace M of a complete metric space X is itself complete if and only if the set M closed. We know by definition of the completeness, if X D is a metric space and here is the set M, and say this is under the induced metric is a metric space, then we say this set M is a complete metric space if every Cauchy sequence is a convergent one. Now, instead of proving this part, we can simply say if a subspace M of a complete metric space, this is a complete given, is closed, that is if I simply prove M is equal to M closure, then automatically it will give you the conclusion that M will be a complete subspace of X. So, you need not to consider the Cauchy sequence, simply say prove all the limits points of the M lies in the M itself. So, that is a very good proof. Let M be complete, suppose. So, what we wanted to show is that M is closed. If it is complete, then M is closed. This is our proof. Now, to show M is closed, then what we show here is that it contains all of its limit point. So, let x belongs to the closure of this. Now, if x belongs to M, then automatically it will be a closed set. Okay, this proof. So, suppose x be a point in there, then because x is in M bar, by the previous result, if x belongs to M bar, then there is a sequence xn in M, this result. If x in M, there is a sequence in M such that xn converges. So, by the previous, so for every x, for every x belongs to M bar, for every x belongs to M bar, there is a sequence xn in M which converges to x. But every convergence sequence is Cauchy. So, xn is Cauchy, is a Cauchy sequence, and M is complete. So, every Cauchy sequence is convergent. So, this implies that xn converges to x is a convergent sequence because it is a Cauchy sequence and the limit point is unique. So, it belongs to M as limit point is unique. Okay. So, this proves M is closed. Now, conversely, if we take M to be closed and xn be a Cauchy sequence, in M, then because Cauchy sequence xn is a Cauchy sequence, so we say xn converges to, and this sequence converges to xa, which is a point in x, suppose. Now, we wanted to x belongs to M bar. Okay. Now, this follows x belongs to M bar by this property. Again 14a, if M is closed, then the situation xn converges to x implies x belongs. So, this belongs to M bar. So, this shows x belongs to M, but M is equal to M bar. So, we get, because it is a closed set. Okay. So, it belongs to M bar. Hence, by assumption, arbitrary Cauchy sequence converges. Hence, arbitrary Cauchy sequence converges in M. So, M is complete. Okay. This completes the proof. Thank you. Thanks. Okay.